Okay, so for this problem, we have a baseball that's moving at 150 kilometers per hour, and it's struck by a bat. So here we have the ball, and it's traveling in this direction, and here's the bat. And the bat is hits the ball, and the ball goes in the other direction, and the ball is now traveling at 350 kilometers per hour, and it's coming at 150 kilometers per hour. So question is, what's the average force exerted by the bat on the ball? And the mass of the ball is given. In order to do this problem, we need to use the impulse equation. And the impulse, forgot the S there, the impulse equation is delta P equals F net delta T. So in order to solve for F net, ask yourself, okay, what's the when the bat is touching the ball, there is a force on the ball, and that force is the applied force. And that applied force is, in fact, the net force. So if you say, all right, the sum of the forces is equal to F net, well, guess what? There's only one force on the ball, and that's from the bat. Now, some people might say, well, what about gravity? It's too small to affect the ball in comparison to the force by the bat. So in this particular case, we'll say therefore that the applied force is equal to the net force. So in that situation, then we can solve for F net here. From this equation, it's going to be delta P over delta T. And now we can replace delta P with delta mv over delta T. But the mass doesn't change, so that's constant, so we can take that out and just simply say this. And if we were to continue along, then we'd say, all right, well, the mass multiplied by V final minus V initial, which is delta V over delta T. And that gives us a mass of, and if you remember here in the question, here's the mass, 150 grams, which is 0.15 kilograms, multiplied by the final velocity. And the final velocity in this case, now we have to get something straight here about our positives and negatives. Which way is positive? Well, I'm going to say that this direction is positive. Okay? That means that the initial velocity was negative. Be careful about that. That's the most common place where students get this question wrong. So in order to convert, by the way, because these values are in kilometers per hour, there's a very simple and fast way to convert. If you have kilometers per hour, all you have to do is simply divide by 3.6, and you'll end up with meters per second. So Therefore, the final velocity would be positive 350 over 3.6 minus, and the initial velocity, right, is to the left, so that's negative. So it's minus negative 150 over 3.6. And then we divide that by delta t, which is, I believe that was given in the problem right here, 0.01 seconds. Now, by the way, 0.01 seconds is 1/100th of a second, but it's also 1 times 10 to the power of negative 2. It's also 10 times 10 to the power of negative 3 seconds. And another way of expressing that would be about 10 milliseconds. So that's actually pretty accurate in terms of, pretty close, I would imagine, to how long a baseball would be in contact. So we'll put that number down here. And now we just have to work it out. And I can do that really quickly. I believe the answer comes out to about 2.08 times 10 to the power of 3 newtons. Now another way of expressing this would be 2.08 kilonewtons. And that's the force. So about 2,000 newtons of force exerted for that very, very short time. That's the average force. And by the way, this is the average force. So if we were to look at a force, applied force versus time graph for the time of 0.1 seconds, it would not actually in reality be a flat line. It would be something that looks like this, perhaps. Okay? So over that time period, the average force might be somewhere around here. And so, well, I didn't really do a very good job of this, but if you look at this area, it should be the equivalent to this area plus this area. And so effectively what I've done is I've said, all right, well, the applied force on the ball, in fact, is when it first touches, it's really low, and it gets bigger and bigger and bigger. And at this point, there is maximum deformation of the ball. So if I was to draw the bat again, like that, oh, bad. But the ball would be deformed because the bat would be hitting the ball so hard that the ball would be kind of ovalized in that instant in the middle here. But the time from, let's say, from here to here would be very short, so 0.01 seconds. But this average force is, if the force was constant, then over that same time period, it would provide the same impulse as the reality does, where the force is actually changing. So there you go. Thanks for watching, and this was our final answer. Average net force.